All right, so let's try this again. So this is going to be the second run through of our strategist final deliverable. Uh, the people presenting for this one will be myself, Carly, and Shuming. All right, so for a quick overview of the project, the goal of the project was originally to just deploy a profitable trading strategy. But along the way, we kind of realized that it would probably be helpful to have a sub-team working on sentiment analysis of stocks, specifically on social media. So the reason why that might be important is because there are like a lot of things that factor into the price movement of stocks. Specifically, like if the public generally thinks negatively of a stock, you would probably expect it to have like a dropping price, right? And then vice versa for positive sentiment and positive price change. So basically, this analysis on the social media side will be more of like a supplement to our trading strategy. So if we see that the sentiment of a stock is negative, for example, maybe we can pause our algorithm. And then if it's like positive, maybe we can artificially inflate it. And yeah, so for the two sub-teams, we have the strategy team and the sentiment analysis team. The strategy team will be mostly working with indicators for their primary strategy, as well as doing some analysis with machine learning. So the two approaches we've tried are a reinforcement learning algorithm, as well as a supervised algorithm for LSTMs. And then for the sentiment analysis side, we tried 3 different models. They're going to be logistic regression, Vader, and BERT, and the 2 presenters will be talking about all these things pretty much right now.
Yeah, I can start on the strategy subteam. And Corey, can you move to the next slide, please? Yeah, so for indicators, this is our indicator method. So for inputs, we have the raw price, that's the closing price. And then we have RSI, which is like this indicator that measures stock momentum. So like if the stock is overbought or if it's underbought. And then we have Bollinger Bands, which is basically like this. If you can see on the picture on the bottom left, yeah, just like this upper band, lower band, and then basically those two are like the Bollinger Bands, and then we sort of compare that to like the current price. So the current price is like above one of the bands, then we know that that's when we buy or sell. And then our outputs, basically this is our metrics, what we measure or how we compare our models. So we have percent return, that's basically how much money we're making. Sharp ratio is return relative to risk. So like say, if we're putting in like overall in GME, then we're taking a huge risk because that might turn to shit. And then we also have max drawdown percent, which is basically also a measurement of risk. That's basically how much money dropped, basically. So for instance, if you are in GME and then GME suddenly dropped to like $1, then that's a huge drawdown percent. Cool, and then can we go to the next slide, please? Yeah, so we also use second derivative because I guess the reasoning behind it was sort of saying that like based on the second derivative, we can see if the graph is like concave up or if it's concave down, and then from there we can calculate, we can predict if like the trend is going to increase, continue to increase, or if it's kind of like slowing down and it's going to drop. Yeah, you see we're basically taking the rate of change twice, and our implementation is just say that, you know, the rate of change, the second rate of change is above 7, then we buy, and if it's below, then we sell. And issues is that this lags behind a lot, because even just based on rate of change, we're looking at like say a 10-day period, and you do that twice, so that's like another 10 days, so that's 20-day period. And there's also like these random spikes in the data, although we could probably smooth it out, or we can clean up the data a bit more to get rid of those. But yeah, because of these issues, we end up not using it. And Carly, if you go to the next slide, we ended up using RSI and Bollinger Bands as our main strategy. And it's basically just combining RSI and Bollinger Bands. So if RSI is high, and then we sell. If RSI is low, the stock is underbought. That means the price will probably go up because more people continue to buy it, and that's what when we buy. Bollinger Band, similarly, like I said before, you know, if it's above the upper band, then the price is too high compared to the average, then we sell. And because we anticipate that the price will return to the average by decreasing. And for our results, as you can see, we made a 4,000% return. This was incredibly good, such that Citadel is actually acquiring us. And so we will be leaving the club and we will be working at Citadel starting in August. I'm just kidding. Okay, so that's actually just GME. But the actual results, we're making about 100% return on this period. I believe these are like a combination of a bunch of tech stocks like Amazon and Google and all that stuff. We have a 1.05 Sharpe ratio, which which is like really good. That's like basically the standard that people will use when comparing these sort of like quant models. And yeah, so that's a really good result. And then some actual results or like some other results. This is on Backtrader. So the previous one was on Quant Connect, and Quant Connect is like this web framework that we can use. And Backtrader is like this Python framework that we're using. And the difference is that like on Quant Connect, we have to use like its own website and like its own libraries, versus Backtrader, it's more of like we could just do everything in like a Jupyter notebook. And yeah, so we basically moved our entire algorithm to Backtrader, and we did some backtraining locally. And this is like, as you can see on the legend, there's like a bunch of tech stocks, Apple, Microsoft, Amazon, Facebook. And yeah, you see that we're starting with 100K, I believe, and then we're ending up with 150, 160K-ish. So that's a really nice profit. The Sharpe ratio is 30. So that's really insane with a 50% net profit. And to compare it, like to give you some contrast, if we hold S&P for this entire period, we would have made about 30% return. So we're making 20% return. We're making 20% more than just S&P. And yes, and then this is another time period in which we did backtesting on, and then during this period, almost all the tech stocks like Amazon, Facebook, they dropped, and then that's what like fucked up our strategy. Was I supposed to swear? Maybe not. Okay, whatever. Okay, but we still got a 20% return, so it's still more than S&P considering that the entire market dropped. But because of that, our Sharpe ratio is a bit low. Cool. And then this is another back test. Sorry. And yeah, this is a bit more than S&P. S&P have about like 146%, I believe. So bottom line is our strategy is consistently better than S&P. And although it might still depend a bit on the market fluctuations. And moving on, we also did machine learning because we're at Launchpad. So we did supervised learning with LSTMs, and then we also did reinforcement learning with A3C stack LSTMs, which I'll explain in a bit. Yeah, so for LSTMs, I believe most people should know what LSTMs are, but in case you don't know, it's basically a form of recurrent neural network, meaning that we feed the state of each network into the next state or into the next network kind of thing. So it takes in a sequence, and we continue feeding it down the sequence. Yeah. So and how LCMs work is actually we have like the state, there's a lot of map, but basically we keep like the state that acts as the memory of the network. And we keep on passing this memory into the next, for the next input, and then we just rerun the same network again. And eventually when it gets to the end, we get an output. Yeah, so for our data, we're using Apple and Tesla stocks for this LSTM. And then we'll also pass in 7 days of past price data. So that means whatever the model only gets the previous 7 days prices. And also we normalize the prices between 0 and 1. And for our results, there's a few gaps here, but for the first graph, you see that's the 1-day price forecast, meaning that basically we predict what the price is for the next day. And so the orange part is the data that we give it, and then the green part and the blue part are I believe the green part is the one we generate, and then the blue part is like the actual baseline, or sorry, it's the other way around. Yeah. So as you can see, it's those two lines are really close, and that suggests that our model is doing really well for 1-day forecast. And the second graph is basically a percent error. So compared to like the first graph, how much area is there between all prediction and the ground truth. So you see it's fairly okay with like it's sort of averaging around 0. So I think that's a really good result. And for 3 and 4, that's what if we feed in like the predictions into the network itself and to get like a sort of a longer prediction. For 3, you see it does really well at the start and it sort of flats out. But if we zoom it in and graph 4 at the bottom, you see that it's sort of overall, like it sort of predicts the overall trend really nicely. And that is our RSTM model. Moving on, we have reinforcement learning, and we're using this library called BTGEM, which I will get to in a bit. So what reinforcement learning is basically we have this environment that we built. In this case, it's the stock market. Well, it's actually not stock. We're doing Forex trading for reinforcement learning. So we're comparing euros and dollars, US dollars. And so the environment is basically the market, and then we pass in like observations, which are basically the state for the agent, and the agent picks out an action, so it can either buy, sell, or hold based on its policy, and that's going to change the environment, and then that's going to in return pass in some sort of reward to the agent, so the agent knows how well it's doing. And also, just a slight detail, we terminate when the agent makes 10% or loses 10% of its entire cash, because if it's too high or too low, then the model will terminate too soon or will never terminate. And so we sort of set this threshold so that it will quickly learn how to make money. And for stack LSTMs, essentially it's basically LSTMs, but we have multiple layers of them. So we feed in the input at the first layer at the bottom, you see where the X's are. And then essentially we take like the output at each cell, and then we also pass it into a different LSTM. And then just like another detail of our model, we pass in the market values, so like the prices into the first layer. And then in addition to like the output of the first layer, we also pass in our portfolio data. So like how much cash we have, what are our positions, like if we can buy more stocks or if we can like sell stocks into the second layer. And then the outputs, I will actually get to it in a bit. Sorry about that. So for A3C, A3C stands for asynchronously advantage actor critic. It's on policy or algorithm that is a bit faster and more robust than say DQNs. And I can break this down. So asynchronously means that we can have multiple agent workers. So on the graph, in like the picture on the left, you can see there's like multiple workers, and this allows us to train the model asynchronously and to speed up basically. So advantage means that instead of just discounted returns, such as in policy gradient, we use advantage to estimate how well the model is predicting its policy. So like essentially it's that we can actually, I think it might help if I explain actor critic first. So actor critic basically means that we'll estimate both a state value and a policy pi. And then we can use our state value V to sort of calculate how well a model is, the policy is compared to like the actual return. So well, I guess it's just like how well a model is doing then versus the expected result that the model is predicting based on its policy. And on the graph on the left, on the right, you can see that's basically the architecture of our model. So we pass in the market values into LSTM1, and then from there we can get pi, which is the policy, and then we continued its output or its state into LSTM2, where we also pass in the portfolio data. And from there we get like a V, the value V, and that's sort of like the critic value. And moving on to results. Yeah, so for results, this is sort of like a graph. You can see on the top, we have like broker cash and all that stuff. But if you look at the bottom, this shows like sort of how the price fluctuates within one simulation. And you can see for the green part, that's when the model is buying. For the red, that's when the model is selling. And you can kind of see that with the model is sort of like buying when it dips and then selling when it spikes up. So overall, this, I believe, made about 10% return, I want to say. Yeah, but this is just one simulation. So we don't have to worry about the details too much on this one. And yeah, so this is the overall return. as you can see, we start at about 2K. So when there's like, it's at, I don't know why it starts at 3K, but on the x-axis. But it's supposed to start with 2K cash. So right about 2.00 e to the third. And so by the end of our training, you can see that it reached about 2.1-ish, so 2100. And that's because we have a threshold at 10%. So it kind of doesn't go too high. And then you can see that consistently increases, meaning that our model is learning to make more money. And honestly, like I think 10% return is really nice because this is, again, over the period of a month. So if you compound that throughout an entire year, that's about 300% return, which is really well. But then again, there are caveats. This isn't a simulation. And also there are a lot of risks because as you can see in the background, there are a lot like these spikes. The reason for the spikes is that the ones in the foreground are actually a moving average. And because we're doing oil, like the results fluctuate a lot. So there are still chances that you're going to lose like all of your money inside a simulation. And moving on, next slide. Yeah, this is the slide. This is like a graph of the reward. As you can see, it's really very similar to the return. And that's sort of expected because with more return, that means the model is making more money and we want to reward the model for doing that. And yeah, so overall, I think our reinforcement learning worked out really well. And I'll hand it over to Billy or Carly, sorry.
Yeah, so the second subteam that we had was the sentiment analysis subteam. As Billy mentioned previously, our goal was to complement the strategy and essentially generate a sentiment for live tweets and also from r/Wall Street Bets to just basically gauge whether a ticker is going to be doing well or poorly, and particularly if it's doing very bad or people have a lot of negative sentiment, we want to pull out our investments. And so our goal is to use sentiment analysis to gauge whether the live tweets and r/Wall Street Bets are positive or negative. And so the first thing that we tried to do is logistic regression. So this is just a simple model using feature engineering with words like buy, sell, string length, punctuation, just very arbitrary things that we just picked that we figured would probably impact the sentiment of a tweet. And so then we trained a logistic regression model on this using a data set that was basically tweets pre-labeled with either a 0 or a 1. Essentially, those meant either negative or positive. And how our actual model ended up going, the training accuracy peaked at around 60% and the validation accuracy peaked at around 40%. So the model wasn't particularly really amazing. And so we moved on to this thing called Vader. And what Vader is essentially a pre-trained model, particularly on social media. And so Vader is already trained to produce sentiment analysis. So unlike a logistic regression where we're coming up with the feature engineering very arbitrarily, Vader has that already pre-trained on social media. And so what Vader outputs is these two factors, polarity and intensity. Polarity meaning whether the output is positive or negative, and the intensity is how positive or how negative. And the reason why Vader is very beneficial for us is because it's able to pick up on cues that show up in social media particularly, and slang terms that we aren't normally seeing in the typical corpus of text. And so here are some of the benefits. Vader is able to pick up on negations, contractions, and also stuff like caps and punctuation, as well as degree modifiers to help with the intensity. And then with slang words, emojis, emoticons, and acronyms, those typically only show up in social media. But since we're looking at those specifically, we figured Vader would be a very good choice to do sentiment analysis with. So here are our Vader results. So here, as you can see, it takes in a particular tweet and then outputs a negative, neutral, and positive score, as well as a compound score of whether this the result is whether the tweet is particularly positive or particularly negative. And then then we would take all these tweets and generate a generic score for each ticker. And the main issue we had was a lot of the scores were mostly neutral, which meant that the results were not helping us to see a strong polarity in either positive or negative. And so a reason why we thought that might have been the case is that Vader is trained on social media, but it's not trained on financial terms. And financial terms is important because there's tweets that will say like, oh, we should all sell or buy at this time. But Vader isn't able to pick up on those cues because it's not trained on what does buy and sell mean. It just is trained on the standard colloquial use of like, you're buying something. But in terms of stock, those are very important words. And so what we switched to was BERT. BERT is a completely different model and it uses transformers. And I will explain that a bit and also explain how we change the data a bit as well. So what BERT is it's also pre-trained on a corpus of text. I believe it's trained, it's a model produced by Google, but it uses a transformer, which uses attention mechanisms to learn contextual relations between words and sentences and in a text. So unlike how Vader and logistic regression just pulled is a bag of words model that pulls the meaning behind each word, BERT is able to actually get context behind what does this sentence mean and how are these two words related. And so BERT has a transformer uses two separate mechanisms, an encoder that reads in the input and a decoder that produces a prediction for the next task. So BERT is often used for prediction of the next word or translation. But here we're going to take the BERT model and the output and actually transform it into a classification. And so there's two components to how BERT works. The first one is an NSP, which is next sentence prediction, which finds the relationship between different sentences. And the other one is mask language model, which finds the relationship between particular words. So as I mentioned previously with attention, that BERT uses attention. Essentially how a very high level overview of how it works is it'll take in these words and the translation. And then for each of the input words, so these are the encoders, it'll create a key. And then for all the decoders, it'll create a query and then dot product those together to create a softmax. And what softmax does is find a probability of, so like say for query 3, how likely is it related to the second word versus the first word or the third word. And by doing that, we're able to train the model and actually get a relationship between words. And essentially what attention does is it's able to pull out what parts of the sentences are important. And also it doesn't have the short-term memory issue that a lot of basic models has. And so, as I mentioned earlier, BERT uses two different aspects. The first one is masked LM. And as I mentioned earlier, this is a relationship between words. And so how BERT does this is it takes in this input and then it takes 15% of the words and then replaces it with a mask token. And what that does is it basically creates a black box for what is word 4 here. So it takes in those 5 words and then masks the 4th word, passes that input into a black box transformer, and then generates an output prediction for what word 4 is going to be. So it predicts the masked words, and then by comparing that with the actual word that's supposed to go there, BERT is able to train and gauge whether it's doing well or not. And then the second part was next sentence prediction. So this is the relationship between sentences, and how BERT does this is it takes in 2 sentences. It takes in pairs of sentences, and 50% of these pairs are related sentences, meaning that one comes after the other sequentially. And then the other 50% are just 2 random sentences with no relationship whatsoever. And so by taking in these two sentences, BERT then creates three embeddings. The first one is just the words themselves. So like, my dog is cute. And then the second one is sentence embedding, whether this is sentence A or sentence B. And then the final one is the positional embedding. So what position does this word appear in this sentence? And it adds in these separators to distinguish like between the two sentences. And so both of these two features, NSP and MLM, are used to in BERT to create this model. And so what we do is transfer learning on BERT. So as I mentioned before, BERT is a pre-trained model. And so it's already trained for us on a bunch of text. And what we do is we take our input, which is we pull the top tweets for a particular ticker. So like, say we want to see how GME is doing, or what the sentiment is for that. We'll pass in this ticker, and using the Twitter API, we're able to pull the top tweets for that ticker, pass that into BERT, each individual tweet into BERT, and then we take the BERT output, and as I mentioned before, it's often used for prediction or translation. So what we get that vector embedding that is outputted from BERT and actually pass it in through some linear layers to actually make it a classification problem. And we add some dropout layers to prevent overfitting. And what our final output is, it's kind of like the Vader output, where there's a positive, a neutral, and a negative sentiment. And so looking at our results, so BERT actually didn't do as great as we thought it would be. And the main reason for this was because BERT usually is trained on a lot more epochs than we were able to do, given the amount of time we had. And so if we were to have more time to train it on more epochs, we would be able to have a better model and essentially have better results. Another reason, another way that we could improve our model would be to have more polarized data to start off with. So a lot of social media, or a lot of text in general is just neutral by default. So a lot of the data that we were training on was majority neutral, and so that I think that was a factor into why a lot of our results were centralized on neutral. But here are some of our BERT results. As you can see, it takes in a tweet, and then it outputs this tensor that this is the negative score, neutral score, and the positive score. So then we're able to gauge how well or exactly how negative or neutral or positive our tweets are, and then we can compile that into general sentiment for a particular ticker. And basically how this ties back into the previous strategy team, and we've mentioned this already previously, but we would take these outputs, and if it's particularly negative, we would decide, oh, we can manually pull out from this investment of this particular ticker. But yeah, those are our three models. Thanks for listening. Does anyone have any questions?